10.4, the second part, is on the arc length. From chapter what? I think it's chapter 8. From chapter 8, we have learned that the arc length is equals to integral from a to b of square root of, maybe instead of a to b, let me just say an interval of dx squared plus dy squared, where our ds is actually the dx squared dy squared. Just like the parametric equation, we will actually change this into alpha to beta for the theta, and we do the derivative respect to theta. Multiplied by differential of theta outside. So what we are going to do is to build what will this formula look like when it comes to polar coordinate system. So we know that x equals to r cosine theta, where the r is the function of theta, right? So dx d theta will be dr d theta cosine theta plus r negative sine theta, while the y is r sine theta, such that dy d theta is dr d theta sine theta plus r cosine theta. I will square both of them. If I square both of them, I will get dr d theta squared cosine squared theta minus 2 r sine theta cosine theta plus r squared sine squared theta. Imagine if I FOIL this. Imagine if I FOIL this. Okay, that's what I get. While dy d theta being squared will be this guy squared plus 2 times this guy times that guy plus this guy squared, right? Remember the formula? X squared plus 2xy plus y squared. So this will then be dr d theta squared sine squared theta plus 2r sine theta cosine theta. I'm actually missing something earlier. dr d theta. dr d theta plus r squared cosine squared theta. Now then, if I add this, notice that the middle term cancels, right? The middle term cancels, and I would have dx d theta squared plus dy d theta squared on the left hand side When I add this, what do I get? I will get dr d theta squared, right? Because sine squared plus cosine squared equals 1. Plus the one here, when I add, I will get r squared. Okay, so my formula for arc length originally now becomes integral from alpha to beta for the angles, square root of dr d theta squared plus r squared d theta. That's the new formula. Now let's use that to compute, for example, to do number 46. Number 46, r equals to 5 to the theta. And the theta is from 0 to 2 pi. So imagine if we have something looks like this. When theta equals to 0, r is 1. So it's actually spiraling. Okay. I don't draw it, I don't sketch it through scale. But basically we need to find the length of that curve. Then how do I set it up? And I need to find first what is r prime, in this case dr d theta. The derivative of exponential is the same function times natural log of 5. I wonder if you remember that. Such that when I square it, I get 5 to the 2 theta times ln 5 squared. Now add that to r squared. I think I do it in the next slide. Add that to r squared. Don't forget, set it up right. This is 5 to the 2 theta ln 5 squared plus 5 to the 2 theta. I can factor that 5 to the 2 theta. Ln 5 squared plus 1, such that the square root will be the square root of that will be 5 to the theta square root of natural log of 5 squared plus 1. Oh, by the way, that's just a constant. So the arc length will then be integral from 0 to 2 pi 5 to the theta square root of natural log of 5 squared plus 1 d theta. But that's just a constant. I hope you remember. So this is square root of natural log of 5 squared plus 1 integral from 0 to 2 pi 5 to the theta d theta. Now, I wonder if you remember how to integrate that. If it is base e, then it's e to the theta. But how if we have different base? Then you need to do change of base first, right? And then 5 to the theta from 0 to 2 pi. Okay, so that will be square root of natural log of 5 being squared plus 1 over natural log of 5. 5 to the 2 pi minus 5 to the 0, 1. That's the solution. Number 48. And this is actually even more interesting. Number 48. R equals to 2 times 1 plus cosine theta. If you sketch this, I wonder if you remember, what will that look like? If you sketch this, what will that look like? When theta equals to 0, that will be 4. When theta equals to pi over 2, that will be 2. Yeah, that's cardioid. So this. Okay. Now, and we basically need to find what is the perimeter of this cardioid. Okay. When I compute later on, I will use symmetry. Okay. When I do the computation later on, I will use symmetry. But let's see what will happen first. I need to be a bit careful here. So our solution d theta will be 2 times negative sine theta, which if I square, it gives me 4 sine square theta. When I add 1, when I add r square, that will be 4 sine square theta plus 4 times 1 plus 2 cosine theta plus cosine square theta. This will be 4 sine square theta plus 4 plus 8 cosine theta plus 4 cosine square theta. Now, I wonder if you agree to say this is equal to, you see that this guy plus this guy equals what? That's equals to 4. Together with this 4 becomes 8. This is 8 plus 8 cosine theta, which I can factor the 8 actually. The thing is, how do we play with the square root? d theta squared plus r squared, that's equal to the square root of this 8, 1 plus cosine theta over like that. Okay, but let's see. Notice that the guy inside is something I think we can play around. This is equals to square root of 8 times 2 over 2 I want to use this cosine squared 2x equals to that will be 1 plus cosine 4x. If this is x here, this is 2x, right? Okay, so if I have 1 plus cosine theta, then this should be 2 cosine squared theta over 2. Is it right? Okay, so So no, I don't need to write it this way. I just need to write it as this is 2 times cosine squared of theta over 2. This will be 4 times absolute. Don't forget this one. 4 times absolute of cosine theta over 2. Yeah, 8 times 2 is 16. Square root of that is 4. Okay, but square root of something squared should be with absolute sign. Now the arc length, therefore, equals to integral from 0 to 2 pi of 4 absolute cosine theta over 2 d theta. That's what it's supposed to be. Now notice that if I don't use absolute sign there, the integral will be 0. Notice that if I don't use absolute sign there, the integral will be 0. Why? Because cosine have this kind of look, but the period for this cosine is 4 pi. Right? Cosine theta over 2 has the period 4 pi. Now, even if you integrate up to 2 pi only, the area here cancels the area there if you don't use absolute sign. Now, once you use absolute sign, then you see the graph actually looks like this. If you put absolute sign. Okay, and the area here is the same to the area here. As we expect, because later on you will see we can just find the arc length here and then multiply by 2. Is it right? It's symmetric with respect to x-axis. Okay. Now, so let me try to benefit from there. So I will have 4 times 2 integral from 0 to pi. Now notice that once I bring 0 to pi, pi over 2 will be still in quadrant 1, where cosine is still positive. That's when we can safely just leave it as cosine pi over 2 without absolute sign. I use symmetry so that I don't need to worry about that absolute sign. Okay, now then this is 8 times the integral of cosine, that's 2 sine pi over 2 from 0 to pi. That's 16. Now, some extra topic, which is important for your calculus 3. Question like number 38. It's not about arc length, but it's about point of intersection. Find all points of intersection of the following curves. Number 38, r equals to 1 minus cosine theta, and r equals to 1 plus sine theta. I think this one is still on the easy side. This one is still on the easy side. Well, if they intersect, then the radius and theta has to be the same. Right? The radius has to be the same. So 1 minus cosine theta equals to 1 plus sine theta. Okay, cancel the 1. So negative cosine theta equals to sine theta divided by cosine theta. We get tangent theta equals to negative 1. So theta must be in quadrant 2 or quadrant 4. In quadrant 2, theta is 3 pi over 4. In quadrant 4, that's 7 pi over 4. Now, then from there, you can plug that in to find the corresponding radius. I think the r for this theta will be 1 plus radical 2 over 2. And this one will be 1 minus radical 2 over 2. So the coordinate in polar will be 1 plus radical 2 over 2.3 pi over 4 in polar, and 1 minus radical 2 over 2, 7 pi over 4 in polar. But I'm not sure that these are the only solutions. Why? The best way actually to graph the curve, to figure out 1 minus cosine theta. 1 minus cosine theta is a cardioid, like that. Okay, that's for the first curve. And then 1 plus sine theta will be something looks like this. No, it's not. It's the other way around. My bad. It's the other way around. It should be like this. Like this. Oh yeah, it intersects only at 2 different places. So this is the first one, the one in quadrant 3, quadrant 2, and then this is the second one, the one in quadrant 4. Not too bad. The tricky one is like question number 40. Because we need to anticipate number 40 or number 42, because we need to anticipate the fact that r may be negative. Let's do number 40. So r equals to cosine 3 theta, r equals to sine 3 theta. If they are equal, then cosine 3 theta equals to sine 3 theta. So tangent 3 theta equals to 1. Right? I divide by cosine 3 theta. Therefore, 3 theta equals to pi over 4 plus pi k. The period is pi. Dividing by 3, that gives me pi over 12 plus pi over k. I wonder if you remember, how many leaves should the first graph has? The radius is 1. That will be, they call that roses, I think. Because it's cosine, they will have 3 leaves because the coefficient is odd, right? Okay, and the radius is 3, so it will go this way, actually. It will go this way. Like that, approximately. Like that, approximately. Okay, while r equals to sine 3 theta will actually comes from here. Now, I think we get confused already. There's so many intersections, you know. Okay, let's find out all of them. Okay, So the first one, when theta equals to, when k equals to 0, we get pi over 12. Theta equals to 1, that's pi over 12 plus pi over 3, that's 4 pi over 12, that's 5 pi over 12. Theta equals to 2, that will be plus 8 pi over 12, that's 9 pi over 12, which is 3 pi over 4. And I go on. The thing is, it has so many intersections that I cannot even figure it out. Plus pi, that's 13 pi over 12. So that's 16 pi over 12. 17 pi over 12. I keep on adding 4, huh? Seems like adding 4 pi. How far do I need to go, Thomas? Well, you will see eventually you hit the same pi again, this one of the solution again. So if I add 2 pi, right, that would be 24 pi over 12, 25 pi over 12, subtract by 2 pi, that would be pi over 12. So what happened is, this guy here is not necessary because it's coterminal with that one. Okay, so I don't need this anymore. So how many solutions we have? There are 12. What are those 12? What are those 12? Can we pinpoint out that here? This is pi over 12. 5 pi over 12 somewhere here. I don't really see it. Okay, 3 pi over 4, I can see it here. Right? And then I have another one here, 7 pi over 4. So I identify this, identify this, identify this. Oh. This one here. So there should be some intersection here. Huh? I have issue with this guy that I have not identified and this guy that I have not identified. Maybe they are too close to the origin such that I cannot see it. But actually at the same time, do you notice that they also have one common point, that is the origin? Right? All of them go through origin. Does that make sense? So one of the common point is origin. Let me write it down. That's when the radius equals to 0. Something that I almost miss, right? Only after I realize, oh, you know what? You know what, that they have radius 0. Okay, so 0, radius 0 for any angle actually doesn't matter. So at least they intersect at 7 different points. Intersect at 7 different points. Okay, let's see if we can find them all. Go to my software. R equals to 1 minus cosine theta. That's what it looks like. And then the second equation, R equals to 1 plus sine theta. Now let me enlarge them. Okay. No, that's not the one. I remember wrong question. One of them is sine 3 theta, and then the other one is cosine 3 theta. Okay, let's enlarge this a bit more. Too big. Put it here. Then I enlarge so that we can pinpoint what are those. And those are pi over 12, and this is the origin. We have this one here. We have this one here. I can only pinpoint 4 of them. Where are the other 3? Where are the other 3? I think it has something to do with the fact that they becomes at the origin. That's 7 over 4. Yeah, 7 over 4. I don't find it though. Well, let's see then. So I can get this one. 3 pi over 4 is identified. And then 7 pi over 12 is identified, but I cannot identify this one actually. Where are those? Let's compute it then. So R equals to sine 3 theta. So 321 pi over 4, and R equals to cosine 21 pi over 4. Is that a question? Where are those? It's more than 2 pi, so let me subtract by 16. That's sine subtract by 8 pi. That's 5 pi over 4. R equals to cosine 5 pi over 4. Should be somewhere here. Okay. Where are those? Am I making this computation somewhere? I'm not making mistake my computation, right? Tangent, that's correct. Yeah, the thing is, again, I only identify 4 here. I only identify 4 of them. I wonder what mistakes I made. I can say that this one here, this one here will give us actually the same result. R equals to sine, if I multiply by 3, that will be 5 pi over 4. r equals to cosine pi over 4 also. So this coordinate, the coordinate for this will coincide with the coordinate for this. At 5 pi over 12. I don't see it here though. I don't see it here. Or is this the 1 5 pi over 12? I mean, I got frustrated because I don't see what I want to see. I get only, so I didn't get this one, I didn't get this one either, but I confirm that this guy give me the same result with, I think this will also give me the same result. And how do you play with these terms to know if you get the coordinate? One of them is pi over 12, right? One of them is pi over 12. So let me change this into pi. Where's my calculator? I need the numerical value of pi over 12. 2618. 0.2618. Let's see. Where is that? Oh, that's the first time they actually hit each other. Remember, it's supposed to look like this, right? So that's the first time they hit each other. So hold on, let me go back to my graph. Notes here. Actually, yeah. So this is my This is my when theta equals to. This is when theta equals to. You know what? I'm using that part. This is when theta equals to pi over 12. Now I need to look, I want to look for where do they intersect at 5 pi over 12. Okay. So what I will do is I change this theta here. I will change this theta here. 5 pi over 12, 1.309. 1.309. 1.309. Where do they meet? Oh, that's where they meet. Okay. So going back to my graph, this is when they meet. This is when they have theta equals to 5 pi over 12. Oh, I see what happened. Now I see what happened. Okay, so I guess this will be 3 pi over 4. I mean, this is clearly 3 pi over 4. This is clearly 3 pi over 4. when I go on to 13 pi over 12, when I go on to 13 pi over 12, pi over 12, 3.403. 3.403. 3.403. Where do they end? I think it will be at one of them. Huh? Where's that? You know what? I make a checklist. I start from pi because the 13 pi over 12 is already more than pi, right? So I start from pi 3.14. It should be pi over 12 one. Yeah. Okay. Now I understand what actually happened. So it hits the same place twice for each one of them. It hits the same place twice. So not that we get it wrong, but this actually becomes when it hits again there at 13 pi over 12, and it hits here again at 13 plus 4, 17 pi over 12, and it hits here again at 7 pi over 12. Oh, I see. I see what happened. It's kind of hard to see how they actually work. So the first time they hit is the first time they hit each other is this. When it goes here, by the time it goes there, it hits first time, bang, and then it hits the second time when this goes this way. It goes here, and this also goes there. One color. Bang. Okay, that's how it works. Honestly, I somehow enjoy doing this, as you can tell, right? Because you have the graph in front of you, but you still cannot decide, oh, which coordinate is this, which coordinate is that. Then how do you detect that using your software? Right? Your software can help you graphing it, but still does not tell you how they move, when they move. So one way to do it is restrict the domain, okay? Such that you can tell, oh, you know what, when theta is pi, for example, they both starts here, going this way, they meet at 13 pi over 12 here. If you try to graph the whole picture at the whole domain, you only see all the places where they intersect, but you don't know when they intersect where. Okay, so that's what I do to see more. So I did detect all those coordinates though. I still detect all those coordinates. It turns out that it is not 7 different points, it's just 4 different points, because the other 3 actually happens at the same place, at the place that we already have earlier. Okay, now for this 14B, I would like you to try the suggested homework. Actually, I'm not really done yet. From this 10.4B, number 37 to 41, number 45 to 47. Number 55 is an interesting question. Number 55. Maybe I do number 56 instead. Find the formula for the area of surface generated by rotating the polar curve R about the line theta equals to pi over 2. So what happened is I have this, okay, and then I have the line theta equals to pi over 2. I'm sorry, theta equals to pi over 2. Oh, no, that's the y-axis. Okay, now we know that if you want to do the surface area with when you rotate with respect to the y-axis. Oh shoot, I'm sorry. Thank you. Am I good right now? Okay, thank you. So number 56. So let's say this is the curve. Let's say this is the curve. Now let's say that's the curve, and I want to rotate this with respect to the y-axis. Now find the resulting curve. I mean the area of the resulting surface. Now, the way we learned it before was like this. We will take a tangent segment, right? We call that ds, right? And then we will, we rotate with this radius x, right? That's the radius. Okay. So the integral will be integral 2 pi x ds. Is it right? And then the theta will be, later on, the theta will be from alpha to beta, let's say, in this case, A to B. The theta is from A to B. Okay, now change this all into theta. This A to B, 2 pi, x will be r cosine theta, right? I hope you realize that I'm just doing substitution. And then the ds becomes square root of dr d theta squared plus r squared d theta. Okay, then that's the formula for surface area if you rotate with respect to y-axis. Here, part B, find the surface area generated by rotating lemniscate of r squared equals to cosine 2 theta. R squared, so part B, r squared equals to cosine 2 theta. Cosine 2 theta. As I remember, it looks like 1. So you should look at this. I think you should look at this. I think you should look at it. Okay, so 2r dr equals to negative 2 sine 2 theta. Cancel the 2, so dr, oh, I'm sorry, I have d theta here. dr d theta equals to negative sine 2 theta over, let me keep it r. So dr d theta squared plus r squared will be sine squared 2 theta over r squared plus r squared. Now I can really just change that r squared into cosine 2 theta. So sine squared 2 theta over cosine 2 theta plus cosine 2 theta. This is sine 2 theta tangent. Don't think it's helpful. Nah, I don't want to do that. Let me do LCD. If I do LCD, I will get sine squared 2 theta plus cosine squared 2 theta over cosine 2 theta, which is 1 over cosine 2 theta. Ah. So what is the square root of that? That's 1 over square root of cosine 2 theta. I don't think I know how to do that one, but okay, so the surface area equals to 2 pi integral what's the angle? From 0 to pi? No, it's not from 0 to pi. 0 to pi over 4. Theta is from 0 to pi over 4 to give me that one. Okay, so what will happen is if I rotate this and double it. Okay, so 0 to pi over 4, 0 to pi over 4, and then I double it. The top and the bottom. 2 pi already out. The x, what will the x be? X will be r cosine theta. The ds will be 1 over square root of cosine 2 theta d theta. And my r is square root of cosine theta. Oh, really nice. My r is square root of cosine 2 theta, which will cancel. So I basically have 4 pi integral from 0 to pi over 4 cosine theta d theta. It's 4 pi times square root of 2 over 2, that's 2 radical 2 pi. Boom. Let's see what is that Lemison look like. Lemniscate look like. R squared equals to R squared equals to cosine 2. That's what it looks like. That's why you see, I don't need to go, if I go back to my curve, you know what, let me correct it. Let me screenshot this. That's why I only move this guy here. I only get this one. That's the one I actually revolve. When I revolve that, you see it will have this guy also, right? Okay. Now whatever I have on the top, I double it, it gives me the surface area at the bottom. So if you kind of like see it from above, if you see it from above, it looks like almost like a donut, I guess. No, I can't really draw it this way. I need to use pencil to actually draw it for you. The thing is, I wonder if I can draw it in 3 dimensions. How will I draw it in 3 dimensions? I think I know what to do. I think I know what to do. Give me a second. I need to. I guess I still use R. Let me give you a break first. Yeah, let me give you a break. Right now it's 8:20 approximately. We come back at 8:30, maybe 8:35. I give myself 5 minutes to figure out how to graph it in 3D. We come back at 8:35. I'm sorry. Thank you. Okay, so I hope whoever read this, they can understand. Yeah, good thing that I'm actually about to start something very important. Yeah, so the first skill that we really need, really need, is recognizing pattern. And I'm about to actually go over things that we don't see in our textbook. Okay, but I myself learned this from my professor at the time, that it would be nice if you see sequence as a function that you restrict the domain, and you relate that sequence to a well-known functions. For example, this sequence here, for example, the sequence that we have earlier here, a sub n equals to 2n plus 1, has something to do with fx equals to 2x plus 1. What do you call that function? Linear function, right? And then how about a sub n of n squared? That has something to do with fx equals to x squared. Okay. How about a sub n of cosine n pi? It has something to do with cosine pi x. Is it right? Now the difference is on the right hand side, the domain is all real numbers so far. Okay. And you can see that, let's say the first one, let me use this. The first one, 2x plus 1, actually a line. That's actually a line. Let's say it looks like this, right? But when you see from the sequence point of view, we always start from x equals to 1. So if later on we graph a sequence, when they told us to graph a sequence, you will see that you can first draw the continuous function, and then you get rid of the, you do the plotting, the dots, and then you get rid of the continuous one. In other words, the sequence must be points on that continuous function, on that function. It doesn't have to be continuous, actually. Right? Another one, for example, when I graph that x squared, the graph of x squared looks like this. Right? That's the graph of x squared. Now then, when x equals to 1, let's say it's here. When x equals to 2, here. X equals to 3 is here. Then what will the graph of that sequence later on? It looks like this. You see what I mean? So imagine that sequence, the graph of that sequence, as part of the graph of the function. Okay, so imagine, then the next thing to do is imagine what is the graph of cosine n pi. Cosine n pi will look like this. Right, and it keeps on repeating. Okay, this is 0, this is at 1, I believe this is at 2, and later on we have 3, right? Is it right? I don't think so. Actually, no, it's not there. It is at 1 here, and this is at 2. Now the thing is, when n equals to 0, it's here. When n equals to 1 is here. When n equals to 2 is here. So the black one is the graph of the function fx, and the red ones are the sequence, the location of the coordinates for sequence a sub n for the third one. Okay, so can you imagine what happens if I use a sub n equals to sine n pi? Sine n pi, it will be like this. Right, that's the graph of fx equals to sine x pi or pi x, right? That's what it looks like, where this is 0, this is 1, this is 2, and on. But then when you limit your x to only integer, when n equals to 0, it's here. When n equals to 1 is here. When n equals to 2 is here. So this is the same to, this is the same to a sub n equals to the sequence of zeros. Now the function itself, the function is not a function of 0 though. It just happened that at 0 and 1 and 2 and 3, the value of that function is exactly 0. Now, I have a name to this kind of function. I have a name to this function. I call that superposition function. That's my terminology. I call this superposition function. That enables us to understand how the sequence actually works by knowing the bigger function first. Okay, that's one technique that we can use later on. Okay, now then, of course, there are more pattern. Another one pattern that I think we need to know is the alternating sequence. That's -1 to the power of n plus 1, for example, when n starting from 1. Which, if I list that, it will be, 1, -1, 1, -1, alternating sign. 1, -1, 1, -1, and 1. Now, one of the challenge is, like what I told you earlier, is can you find the sequence, the formula for the sequence by looking at that? Okay, let's play more. I guess this is example 2. Suppose first one, if you see this sequence, if you see the sequence of 2 over 3, and then 3 over 5, 4 over 7, 5 over 9, 6 over 11, and so on. Can you tell what is the general term for this sequence? You see the top one start from 2, it increase linearly, right? You keep on adding 1, keep on adding 1, keep on adding 1, as if we are having y equals to x plus 1. Is it right? When x equals to 1, you start from 2, and the slope is 1, right? Okay. So then when I put it here, it will be n plus 1 instead of using x. Okay. Now, while on the denominator, you notice that you keep on increasing by 2, right? So it must have something to do with the slope equals to 2. Y equals to 2x plus something. When x equals to 1, the y should be 3. So it's 2x plus 1. Right? Then this will be 2n plus 1. Now, if you want to check, check this one. This is n equals to 5, right? So what is a sub 5? A sub 5 is 6 over 11. Bang, you are done. Now, what I don't want to happen, of course, somebody look at this and still say, oh, you know what? Let me find what's the slope. Right? You look at that and you cannot really tell the slope by just looking at it. I don't know how to help you. Another one. Let's make it more complicated. Suppose I have -3 over -3 over 5 positive 2 over 25 -1 over 125 and then 0 and then negative positive 1 over, I don't know, it's too big. Can you tell the formula? The way I see it is alternating. Minus, plus, minus, plus. No, it's supposed to be minus, but maybe the minus disappeared because that's minus. Notice that the top here is decreasing one by one. 3, 2, 1, 0. I guess they should be negative 1, right? So to play with the alternating, that's negative 1 to the n. When n equals to 1, that's negative. Okay, and then the slope here on the top, you start from 3, going down one by one. So it must be y equals to negative x plus something. When n equals to 1, it is 3. When x equals to 1, that's 3. So it is 4 minus x. So this is 4 minus n. And on the denominator, 5 squared, 5 cubed, you can assume this is 5 to the 4th here. But because 0 on the top, it is still 0. This is 5 to the n. Let's do some problem first. I really want to go fast such that we can go to the core of this section. But I also understand plenty of you, when you took Pittacus, you may not go this far. You can only do well if you do a lot of examples though. Okay, let me see from number 8. Write the first 5 terms where the formula a sub n equals to negative 1 to the n of n over n factorial plus 1. Now, n factorial, by the way, means n times n minus 1 times n minus 2 all the way down to 1. So, for example, 5 factorial means 5 times 4 times 3 times 2 times 1. Okay, so can we write the first 5 terms? What is a sub 1? Negative 1 to the 1 times 1 over 1 factorial plus 1. That's negative 1 over 2. The second term, negative 1 squared times 2 over 2 factorial plus 1. That's positive 2 over 2 plus 1 is 3. A sub 3, that will be negative 1 cubed times 3 over 3 factorial, that's 6 plus 1, that's 7. So that's negative 3 over 7. A sub 4, that will be positive 4 over 4 factorial, I think that's 24 plus 1, that's 25. So a sub 5 will be negative 5 over, you see we have alternating. We have alternator, right? That will make it alternate plus minus, plus minus, plus minus. Okay. The denominator, that will be 5 factorial 121 plus 1, right? So the sequence basically negative 1/2, positive 2/3, negative 3/7, positive 4 over 25, negative 5 over 121. How about number 10? Number 10, we have recursive form. the first term is 6. The next term equals to the previous term over n. So the first term, and do here, the first term is 6. The second term is the previous term over the n, which is 2, that's 3. The third term is the previous term over 3, that's 1. The fourth term is the previous term over 4. The fifth term is the previous term over 5. So the sequence will be 6, 3, 1, 1, 4, 1 over 20. Number 12 is actually quite interesting. Number 12, the first term is 2. The second term is 1. The next term is the previous term minus the previous term. So the first term is 2, the second term is 1, the third term means the n equals to 2, right? The n equals to 2. That's equals to a sub 2 minus a sub 1. The fourth term means a sub 3 minus a sub 2. A sub 3 is -1 minus a sub 2 is 1. A sub 5 will be a sub 4 minus a sub 3. A sub 4 is -2. A sub 3 is -1. And so on and so forth. So this is the recursive one. Number 14. Find the general formula. 1, -1/3, +1/9, -1 over 27. This one is not fun. 1 over 81. Can you help me? What's the formula? First, take a look that it is alternating. Start with plus, right? Start with plus. So if I use -1 to the n and my n equals to 1, that will be negative. To make it start from plus, either you use n minus 1 or n plus 1. That will make it positive. Start with positive when n equals to 1. Okay, now the numerator is always 1. The denominator, you can see this as over 1, 3, 9. So the base, you keep on multiplying by 3, right? That's kind of like 3 to the n thingy on the denominator. Okay, but I need to start from exponent 0, so I minus 1 here. Okay, so I get 3 to the power of n minus 1. Or you can simply say -1 to the power of n plus 1 over 3 to the n minus 1. Now, if you want to simplify that further, just in case, I'm usually fine with this answer, but you know that you can simplify that a little bit. This is 3 to the n times 3, right? So it is actually reasonable for you to write it this way: -3 times -1 to the n over 3 to the n. That's also okay. Can you think of number 18? The sequence 1, 0, negative 1, 0, 1, 0, negative 1, 0. I give you a hint. Start this way. Where the first, when n equals to 1, it's 1, n equals to 2 is 0. Like that, right? Do you see that pattern? Then play around with that. I think this is sine. Is it cosine? Cosine pi over 2 will be 0 all the time. You need to have the counter n. Sine, yeah. I think it's sine also. It's sine. But you don't forget, you need to have the counter though. N pi over 2. So when n equals to 1, that's 1. When n equals to 2 is 0. When n equals to 3 is negative 1. Right? And starting from 1. Now, that sequence usually written this way. Sine and pi over 2 n equals to 1 to infinity. There is a convention that you can just write it this way if it is clear that the counter is n. Okay, in fact, going further, it is understood that you start from n equals to 1 if you don't write anything. That's convention. In other words, you have to write what your n start with if you don't start from 1. Okay, now let's go on with the core. Why do we want to learn sequence? The main reason we learn sequence is because we want to see if it is convergent or divergent. A sequence definition. A sequence AN has the limit L denoted by limit n goes to infinity of a sub n equals to L, or I don't really like this notation, as n goes to infinity, a sub n goes to L. If if there is a number n such that the distance from the nth term and L is less than epsilon for any n greater than that number n. If for every epsilon. Now let's try to explain this. I think I want to explain it from the point of view of the superposition function first. Suppose I have this function. Now, it is clear that this is the limit of that superposition function. Now, your sequence may be moving this way. Imagine if I get rid of this. You see that? Okay. Now, what this definition says is the following. That whatever epsilon you choose, let's say I choose epsilon this big. So this guy here is L plus epsilon, and this guy here is L minus epsilon. Now, for any epsilon you choose, there must be the number n. There must be a number n. Like in this case, this is my n. Such that whatever term coming after that, it must stay, these points here must stay within the band, within this strip. Now the thing is, this epsilon has to be for every epsilon. So you can make the epsilon small, even smaller, and of course your capital N may move further to the right. You see? Okay, so let's say we experiment with that. Suppose I make my epsilon even smaller, half of that. I make my epsilon even smaller, half of that. And from here, I see that my capital N now will start from here. Such that any terms after that will stay within that band. Now, if you can find, if that sequence has this property that you can choose any epsilon, every time you choose an epsilon, you have that capital N, such that any terms coming after that will stay within that band, within this strip here, then the limit exists, and therefore convergent, and the limit is L. Okay, what I did here is to give you the pictorial mindset about what the limit should be. Okay, now there comes a big theorem that says the following. Theorem, I call that superposition function theorem. Superposition function theorem. That says the following. If Fn equals to the sequence. If you limit the function, to integer domain, and the real function instead of just integer function has the limit L, then I think I should say as x going to infinity, then the sequence also convergent to L. Now the graph that I need is basically the one up here. Notice that the bigger function, you can see here, the bigger function has horizontal asymptotes L. Right? Okay. So the points, which is part of that graph, as you go further to the right, must also converge to the same L. Well, because these points here, actually part of the graph. If the whole graph actually converges to L, then these points should also converge to L. Okay. Now, we will use that later on. We will use this later on. But some words that if we have limit n goes to infinity of the sequence and this is equals to infinity, we still say that this is divergent, but this is divergent in a special way. Okay, so we say that means a sub n, that sequence is divergent to infinity. It's different type of divergence compared to if we say this one, limit n goes to infinity of cosine n pi. This is divergent because the limit does not exist. Okay, so cosine n pi is divergent, but not divergent to infinity. In fact, we can say that cosine n pi will be equals to -1 when n is odd and 1 when n is even. Right? If you think about it. So this is actually the same to the alternating functions, that is -1 to the n. Limits law of sequence. Limit laws of sequence. It basically follows the limit that we learn in Calculus 1, the limit laws that we learned in Calculus 1. At that time, I believe we called it limit laws of functions. The first one, basically, sum of limit of sum equals to sum of limit. Limit n goes to infinity of the first term plus the second term equals to the limit of the first term plus the limit of the second term. Actually, I need to say if a sub n convergent to, let's say, a and bn converges to b, then the limit of sum equals to the sum of limits, which will give us a plus b. Actually, it works the same way if it's minus. Second, limit of constant multiple of a sequence equals to constant multiple of the limit of that sequence, that's C times capital A. And of course, limit of a constant term is just constant, nothing fun with that. I think of that as a constant function. Now, limit of product of sequence equals to product of limits of sequence. And the quotient is also true. Limit of quotient of sequence equals to limit quotient of limits of sequence. Of course, that this is equals to a over b, given that b is not equals to 0. Okay, otherwise it becomes undefined. The same way with exponent. Yeah, the same way with exponent. Okay, but here it says just for technicality that p and the sequence has to be positive. More. More. Limit n goes to infinity of a function of a sequence is equal to the function of the limit of the sequence. For fx continues. At a. Yeah, that's something nice to know. Others, squeeze method, squeeze theorem basically. Let's say the sequence B is bounded above and below by sequence A and sequence C. For n after certain n. And A sub n, C sub n both convergent to the same number called that A. then B must be convergent to A also. Basically, you squeeze that. Imagine that from function point of view. So let's say this is the one function and this is another function. No, I don't like it. And B has to be living in between these two guys. Then, of course, eventually, B must be in between that A and C, which limit both of them equals to A. That's because of this. That's because of this. So if A sub n less than equals to B sub n less than equals to C sub n, if you apply the limit, and it happens that the left-hand side, the limit is A, and the right-hand side also have the same limit A. Then consequently, the limit of Bn, the Bn converges to A. Okay, I basically use squeeze theorem. The last one, I throw at you all those properties at once, basically. The last one, limit n goes to infinity of absolute A sub n equals to 0, means the sequence is also convergent to 0. Okay, I prefer to write it this way. If the absolute sec of the sequence goes to 0, then the sequence itself must go to 0. But what we have here is actually a consequence of squeeze theorem. Yeah, because the proof for this is actually quite easy. Let me just do it. So you see that A sub n must be less than equals to absolute of A sub n, also bounded below by negative absolute of A sub n. Now the thing is, when n goes to infinity, this becomes 0, this becomes 0, right? So the only way that can happen, we can tell about the limit, the A sub n, it must be because the A sub n goes to 0 also. This is not true if the absolute is not 0. Warning. Limit n goes to infinity of the absolute of n if equals to constant, it does not imply that limit n goes to infinity of that sequence A sub n will be C. No. One good example, of course, the alternating sequence. Because that's the counterexample, right? To show that it is not true. Notice that absolute of A sub n is equals to 1, and limit n goes to infinity of the absolute of the sequence is 1, but limit n goes to infinity of the sequence itself does not exist. Yeah, more things need to be said here, but let's start working on some problem. Number 24, for example. Determine if the sequence is convergent or divergent. A sub n of n cubed over n cubed plus 1. How do we prove that this is convergent or divergent? Solution. We do the limit, right? Limit n goes to infinity of this sequence n cubed over n cubed plus 1. If you plug in n goes to infinity, you get infinity over infinity. Warning, a sequence is not a continuous function. So we cannot apply L'Hopital rule directly. Okay, so do not apply L'Hopital rule. Don't do here, oh, you know what, I applied L'Hopital rule, so I have limit of 3n squared, blah, blah, blah. No, 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 no. Okay. But on the other hand, we actually have, I can think of 3 different ways to do this, and 2 of them actually quite similar. The first method, I attack that sequence directly, but of course I use the limit rules. So on the top I divide by n cubed, at the bottom I also divide by n cubed. So this is equals to limit n goes to infinity of 1 over 1 plus 1 over n cubed. Then when n goes to infinity, I get 1 over 1 plus 0, which is 1. That's the first method. The second method, I will use the superposition function theorem. So I will say let fx equals to x cubed over x cubed plus 1. Now make sure that this function is continuous, at least when x really, really big. Okay, note that fn equals to n cubed over n cubed plus 1, which is our sequence. Now, consider the limit. Limit x goes to infinity of fx equals to following what we did earlier, right? I divide by x cubed on the top and the bottom. Actually, the idea of dividing by x cubed was stolen from here, actually. Yeah, the one we did in the first place, the one I wrote in black, is actually coming from here. It's 1 over 1 plus 0 equals to 1. So, by superposition function theorem, limit n goes to infinity of n cubed over n cubed plus 1 also equals to 1. the third method, you know what, the third method, let me steal it from here. The third method, I continue from there. Notice that the function is continuous right now. So I can now use L'Hopital rule. This is what I meant earlier when I say you cannot apply L'Hopital theorem directly. You cannot apply L'Hopital theorem directly. You need to go through superposition function. So if I apply L'Hopital rule, I get, and you may want to apply it 3 times. I don't think so. I don't think I need to apply it 3 times. Let's limit x goes to infinity of 1, therefore that's equals to 1. So by superposition function theorem, limit x goes to infinity, n cubed over n cubed plus 1 is 1. Number 30. The sequence is the square root of n plus 1 over 9n plus 1. So limit n goes to infinity of square root of n plus 1 over 9n plus 1. That's equals to square root of the limit. Now you don't have to do it in this order though. The main key step is actually dividing the numerator and denominator by n. Right? So be 1 plus 1 over n, big over 9 plus 1 over n. That will be square root of 1 over 9, which is 1/3. I think you can just keep the limit outside and you are fine. Number 34. A sub n is equal to -1 to the n plus 1 of n big over n plus square root of n. I wonder how to do this one. I think this is divergent though. But let's see. This is limit n goes to infinity of -1 n plus 1 of n over n plus radical n. Let me divide the top and the bottom by n. So the top will get 1. At the bottom, I get 1 plus 1 over square root of n. So you can say this is equals to limit n goes to infinity of -1 to the n plus 1 times limit n goes to infinity of 1 over 1 plus 1 over radical n. Now that one will be 1. But this is not convergent. This does not exist. So the sequence -1 to the n plus 1 times n over n plus square root of n is divergent. The sequence is divergent if the limit does not exist, or infinity, or negative infinity. Number 40. I do a lot of problems today. Number 40, the sequence tangent inverse of n over n. Does the limit exist? Does the limit exist? Well, I can say that tangent inverse n will be always between pi over 2, not including pi over 2 actually, between pi over 2 to negative pi over 2, right? It's tangent inverse, not tangent. Tangent inverse, it's like this. It has the upper limit, and it has lower limit, right? Okay, now then divide this by n. Okay, for sake of simplicity, let's put equal sign 1. It's not wrong. We know it's never equal, but I can just put it like that. Now apply the limit. We get this is 0. Limit n goes to infinity. Tangent inverse of n less than equals to 0. So by squeeze theorem, limit n goes to infinity of tangent inverse n over equals to 0. Suggested homework from this 11.1a. I need you to do actually you should be able to do up to number 55, number 1 to number 55. Try to do this. Okay, that's for today. See you then on Monday.